So you should be seeing my mouse, I hope, and hearing me. All right, excellent. So the title of this talk is an overview of recursive proofs. The goal that I would like to achieve today with this presentation is first and foremost to explain what are recursive proofs, in particular motivate them. And the reason why I chose this topic is that over the last couple of years, this notion of recursive proofs that I will explain has transitioned from a topic of primarily theoretical interest and maybe a little bit of applied interest within the researcher community into a technology that has been put into production by several open source projects. And while there are, in my opinion, good high-level descriptions of recursive proofs out on the internet, there is very little in the way of material for learning about the science behind the recursive proofs. So with this talk, I would like to talk a little bit about the foundations of recursive proofs from the perspective of a cryptographer. So with that, let's get started. In order to explain what are recursive proofs, I have to first tell you what is a succinct non-interactive argument, okay? You may have seen already this notion. It goes by the acronym SNARG. These are cryptographic proofs for computation correctness whose size is exponentially smaller than the proof computation. So how does it look? Here's a diagram for it. You have two algorithms. You have the prover and you have the verifier. The prover wishes to convince the verifier of a certain statement. Here it is. Given a circuit C and a public input X, the prover wants to convince the verifier that it knows a witness W, usually secret, such that the circuit accepts the input X and witness W, okay? And the key efficiency property of SNARG is that the proof used to convince the verifier is much, much smaller than the circuit and the witness. It is polynomial in the logarithm of the size of the circuit and some security parameter. All right, so this is what is a SNARG. Often you will see SNARGs discussed together with the notion of public parameters, also known as a setup. I will not, this is an important distinguishing feature between different SNARG constructions. I will not focus on this much today, so this will kind of disappear and will not be concerning us throughout most of this talk, though be mindful that this is there. All right, so that is a SNARG, just mostly as a recalling for you. I would like to now motivate the recursive proofs. So let's say that you would like to prove the iterated execution of some function f. So you're given some f, some number of iterations t, and some claimed output zt, okay? And you would like to prove that by applying iteratively the function f t times, let's say, to some input 0, you obtain zt. Okay, for now, this is a bit of a silly computation, but bear with me for a moment. One way you could try to prove this is through something we could call the monolithic option. You prove all t executions at once. What does that mean? It means you take a SNARG and you ask the SNARG, say, please prove to me all of these t invocations of f all at once in one big computation. This you can go ahead and do. However, there are two problems with this. One is that this may be infeasible. Like if t is large enough, because most SNARG prover implementations have memory usage that grows with t, at some point this is just going to be infeasible. It's just not going to fit even in a huge machine. Another problem is that t may not be known in advance. It actually could be that this f of f of f of f is just some ongoing or everlasting computation, and there is no final t. It just keeps on going. So an alternative option that you could imagine is something you could call recursive option. Essentially, it means that you prove one execution and also prove the correctness of a prior proof. So visually, it would look something like this. First, you prove the first application of f, obtaining some intermediate output z1. So you prove that z1 equals f of 0. Then you prove in a second step that f of z1 is z2, but also you prove that you have checked the prior proof, and so on and so forth. Okay, So this kind of continues ongoing, and at any moment in time, the verifier can check that for the current time step, the current output and the current proof are correct. And inductively, because each time you were checking also the prior proof, you would know that there is a sequence of intermediate outputs that lead to the current output. So the main efficiency advantage here is that you're invoking the snark on a small, teeny tiny statement, the size of f, and you're just repeating this algorithm over and over. Okay, and this simultaneously addresses both of the above problems. There's no large memory requirements because you're invoking the snark on a small statement. And also, you don't need to know t in advance. If like t needs to be bigger, you just keep on going. So this sounds like interesting, but it's just like some pictures right now. So what I want to address today is, to what extent is this secure, and is this even efficient? And to motivate this idea, to talk about this idea, we're going to have to talk about what we are trying to construct. We have a snark. We have this high-level construction in mind of just applying the snark recursively. But from a cryptographic standpoint, what are we trying to construct? Cryptographers have put forward a notion that captures this notion of everlasting computation you can check through something known as incrementally verifiable computation. So more formally, you could say that an IVC scheme for a transition function f, the function f that we were discussing earlier, is also a tuple that consists of a prover and verifier, but has a slightly different interface than a snark prover and verifier. Here, the prover will take as input the prior output and the prior proof, and it will produce a new output, a new proof that the verifier can always check. But crucially, you can reuse the outputs of the prover to produce more outputs and more proofs. Okay? And actually, in many applications, it is actually important that every time you recurse, you can have the option of giving the function f some local witness. I'll give that as an example later. But slightly more precisely, what you would like to say is that you can always make progress if things are good. In other words, if you give me some good transition, namely the next output really is the output of the transition function f, and you give me prior inputs that the IVC verifier accepts, then it is possible to construct a new honest proof using the IVC verifier that the IVC using the IVC prover that the IVC verifier would accept. Now, this would be rather trivial to construct if it wasn't for the main efficiency property that we want out of this primitive, is that you want each recursive proving, like each time you apply the IVC prover, you should only pay for the local computation f. And the proof size also should be maybe as large as f, but these things should be essentially independent of t, okay? So even though there's like a long chain of applications of f in the past, now you're doing one more iteration of f, and applying the honest prover and the proof that you produce don't depend on the long chain of computations in the past, okay? This makes this task very non-trivial. Now, from a security standpoint, of course, we also want some security. And intuitively, what it is that you want to achieve is that if somebody gives me, so hey, here's a claimed output and a claimed proof, and the IVC verifier accepts, then we want a security guarantee that there are local witnesses in the past that at every time step produce Z1, Z2, Z3, Z4, up to all the way to ZT correctly according to F. Okay? So this is the notion of incrementally verifiable computation. In cryptography, we also consider generalization known as proof carrying data, where essentially we consider functions f that takes multiple inputs, not just zt minus 1, but also zt minus 1 prime, double prime, and so on and so forth. This lets you express computations that evolve not on just a line graph, but on directed acyclic graphs. Now, why do we care so much about incrementally verifiable computation? Well, there's many applications. First, actually, you can actually think of incrementally verifiable computation as a stepping stone to constructing snarks with excellent space complexity. So there are certain regimes of snarks that we only know how to construct by basically starting with an inefficient snark and constructing IVC and then obtaining a better snark. This is known as snark bootstrapping. You can also use incrementally verifiable computation to construct snarks for distributed computations like MapReduce, where the proving process is itself a distributed computation, namely it's itself a MapReduce computation. You can construct primitives that are important in the blockchain space, for example, verifiable delay functions using IVC. You can also construct succinct blockchains. These are blockchains where each state transition is accompanied with a succinct proof that the state was obtained correctly from the genesis state. This leads to ultra lightweight clients. So there's lots of applications to incrementally verifiable computation. So hopefully this is something that I've convinced you it is worth shooting for. Now I would like to discuss how do we construct incrementally verifiable computation schemes. So as I have already alluded to at the beginning of the talk, the high-level idea is that we're going to use the snark prover to prove something about the state transition as well as this snark verifier. Let's look into that into more detail. So from a cryptographic standpoint, we are starting, somebody hands us a snark scheme, and from it, we want to construct an IVC scheme. The crux of the construction for this step is to define let's call it a recursive computation, R, okay? R stands for recursive, that checks that a new output satisfies the IVC function f, okay, the state transition, and the prior output and proof satisfy the snark verifier. So here it is. So I define the recursive computation R. It takes as input a new claimed output, ZT, as well as some auxiliary witness. The auxiliary witness contains the prior input and the prior proof, as well as the local witness. And it does the things that we just said it should do. One, it should check the state transition. And second, if we're not in the base case, it runs the snark verifier, notice on itself, okay? So this is going to look temporarily confusing, but this apparent circularity can be resolved. It runs the snark verifier on itself, checking the prior input and the prior proof, okay? Now, once you have this recursive computation defined, constructing the IVC prover and the IVC verifier is rather straightforward. Here they are. The IVC prover will simply assemble this recursive computation from the transition function and the snark verifier, and it will just use the snark prover to produce a proof that the recursive computation has accepted the new output ZT. And then you just output the snark proof. The IVC verifier also is similarly straightforward. You assemble you construct the recursive computation from the state transition and the snark verifier, and then you just run the snark verifier, checking that on this computation, this was a correct and accepting input. Okay? So from a syntactic standpoint, this is basically the crux of the construction from going from a snark scheme to an IVC scheme. So now we should ask, is this secure? So a few years ago, it was proved that from a security standpoint, if the snark is a so-called adaptive argument of knowledge, this is what you typically see being referred to as a snark with a K in the end that refers to this argument of knowledge property. I'm not going to go into detail, just some cryptographic requirement that strengthens the security of the snark. Then whatever I've shown in the prior slide essentially is a secure IVC scheme. The other important part is that the efficiency property of the snark of the IVC follows provided that the snark has so-called succinct verification. This means that running the snark verifier is much faster than the circuit that you're checking. Okay? And intuitively, this is because if it wasn't the case, then the recursive circuit would have to grow in size at each step, and we wouldn't have the efficiency properties that we wanted. So this holds more generally also for PCD schemes. And so we have a theorem that says that if anytime you give me a snark with succinct verification, I can apply the construction and I will give you back some IVC or PCD scheme that corresponds to it. Now, if we take a step back, this very same construction actually preserves important properties. So, for example, if the snark was zero knowledge, then the IVC scheme that you construct is also zero knowledge. This is important for a number of applications. Also, for those of you that are familiar with the intricacies of snark setups, this transformation preserves the type of setup. Like if you start with a nice setup, like for example, if it is updatable or transparent, again, I'm not going to explain what this means. These are just nice properties of a setup. Then you get IVC that has the same very nice properties. Okay, so kind of this construction is quite sort of behaves well with nice properties of snarks. Now, from a theoretical standpoint, requiring a snark to be an adaptive argument of knowledge is pretty it's a pretty strong requirement. However, in practice, most snark constructions satisfy it, rather easily. So it's not really like a restriction. I mean, it's mostly an important theoretical consideration, but most constructions we care about already, like you need to work a little bit, but you can fulfill this property. The fact that we need to require the snark to have a succinct verifier actually severely restricts our choice of snark. There are some really nice snark constructions out there that have excellent properties, but they're just not succinct. And so we can use them for a number of things, but recursion as is doesn't seem to be one of them. So this is going to motivate the second part of the talk. I'm going to pause for a moment here because there was a question that I just noticed. The question was, how can we generate the computation R? So I'm going to come back to the computation R here. So I presume the question has to do with the circular nature of this one. So if R were a circuit, then how could the circuit include a description of itself, right? This can be resolved because typically in snark constructions, the verifier doesn't actually receive the circuit as input, but it receives a cryptographic commitment to it. So the way you would actually create this R is that you would say, actually, R receives as input not just ZT, but also some generic commitment. That generic commitment will be kind of given as an input to the snark verifier. And then in action, you would use R and you would give as input to it a commitment to itself so that that commitment would find its way here. And that's one way. There are other ways to kind of break the circularity. The rest, you just assemble it. You have a circuit for F, you have a circuit for V. Together, they make a circuit for R. And I hope that answers the question. Okay, so I'm going to come back to this slide. And
hey, before you move on, can I ask a question?
Yes, of course.
How do you define the security here? What is the attack model?
So the security of IVC is, let me kind of go back to this slide. It's actually not that complicated to define. It's even harder to define than function. It's even easier to define than functionality. So somebody comes and says, here is a string that claims to be the output of applying F to itself T times. And here's a proof that certifies that. Now, of course, if this is like a proof that doesn't validate, then you can tell this person to go away. But if it does validate, then now you want some guarantees. The guarantees says the following, that you can efficiently extract, you're using some cryptographic extractor from the malicious prover, witnesses, T witnesses, such that they basically witness correct transitions leading up to ZT. So you can go from some standard initial state Z0 to Z1, thanks to the witness W1, then to the state Z2, Z3, Z4. You can think about it as basically just a machine computing that has some non-deterministic advice at every time step, W, and you want to make sure that ZT is a valid Tth state of that machine.
Gotcha. Yeah, thanks.
Yeah, great. Thank you for the question. Okay, now coming back to where we were. Basically, so here we learned that if you give me a snark with succinct verification, then I'm able to construct this IVC notion from it. This is a fine theorem, but there's something that is kind of annoying, which is we have good constructions of snarks, in fact, snarks, that, however, do not have a succinct verifier, and we would like to use them for recursion. So this brings us to the next part of the sort of foundations of recursion, relating to so-called accumulation. Let me explain what it means. Just last year, there was a very nice paper that observed that really, for recursion, it should be enough to incrementally update a state that remembers the conjunction of a validity of past proofs. You don't really need to check all the past proofs. You just need to remember the conjunction of the validity of the past proofs. And then you can always check this conjunction outside the recursive circuit. Okay, this sounds like maybe potentially confusing, but we'll have lots of pictures to kind of clarify this. And in a paper earlier this year, the suggestion actually led to progress on the foundations of recursion. And for that, I need to first explain what is a snark with accumulation. Before we were using a snark with succinct verification. Now I want to explain what is a snark with accumulation. I'm going to use first a picture for that. So we say that PVD, written in this Blackboard bold, is an accumulation scheme for a snark PV if the following happens. So on the one hand, we are interested in looking at many snark proof verifications. So this is the snark verifier checking some circuit, accepting input and proof, checking some proof pi1 that certifies that the circuit accepts x1. Intuitively, this is the snark verifications that we wanted to check recursively at each time step. But remember, now we may be in a situation where the snark verifier is not succinct. So maybe this computation is very expensive, okay? So instead, we're going to consider a different process, an accumulation process. So you have here the accumulation prover that takes some accumulator, throws in the next instance and proof, and produces a new accumulator, and so on and so forth, okay? And what is the guarantee? Is that if you check that each accumulator was derived from the previous one correctly, this is the accumulation verifier. Here's another accumulation verifier that links these two. Here's the last accumulation verifier that links these two. And you have the accumulation decider that checks the next one. Then these two processes are the same up to, cryptographically. Essentially, it is, if you want to check a bunch of snark verifiers, it is tantamount to checking that all the accumulations were done correctly and the last accumulator passes the decider's predicate. Crucially, we want this accumulation verifiers to be very small, okay, to be succinct. But we do not require the accumulation decider to be small. Intuitively, what's happening is the verifiers are just accumulating the conjunction of all these things, and the decider is checking the conjunction of all these things. And because the verifier is not succinct, the decider is not succinct either. But that's okay, because we will be using the fact that the verifier here is succinct. Again, here the intuition is that we're going to have a way to remember, to succinctly remember the conjunction of the validity of past proofs, but we haven't checked the conjunction yet. We'll check it later on using the decider, okay? So that's the picture of an accumulation scheme for a snark. I haven't said why it's helpful for recursion. I will do that in the next slide. But actually, let me maybe pause for a moment and see if there are questions about this notion. Also, if you've heard of set accumulators like RSA accumulators, it's unrelated. It's just, we had to choose between, this is a paper with some of my students and Benedict Bunz. We had to choose some name. There was, batching, aggregation, accumulation. We chose accumulation, but it has nothing to do with set accumulators. the question is, so there's a question that says, will T be an input to the accumulation scheme? No, T will not be an input. Just like in recursion, T is just some ongoing process. So I could stop anywhere here and use the decider and know that if all the accumulation verifiers are so far accepted and the decider accepted, then I know that all the snark proofs that were accumulated so far did verify. So this is an ongoing process. You can think about it, there's a stream of input proof pairs that come in, and I keep accumulating them into my latest accumulator. And at any moment in time, I can use the decider to check the latest accumulator, provided that somebody did the check in the past, recursed away all the succinct accumulation verifiers. Hopefully that answers the question. Let me see if, let me just wait for a few seconds in case there are other questions. Okay, so if not, what I want to do now is I want to explain how this notion of, so there's a question that says, is it suitable if A0, A1 are internal and so on are internal states? I would like the X's really are the internal states of the machine. These eventually will become the Z's that we were thinking about. A is going to be basically values passed on from the IVC prover to the next IVC prover. So, I mean, they're using the internal states of the computation of the iterated function f, but they're just whatever the accumulation scheme decides to be, right? Okay, I don't see more questions for now, so let me proceed. I will now explain how to use this thing together with a snark that possibly doesn't have a succinct verifier to construct, again, IVC. I actually like this picture very much, and I'm going to skip the textual. I mean, just before this talk, I had the text, and I decided I needed a picture. So I'm just going to skip the text because I think in the picture it was clear enough, and this will just take us too far afield. So this is just text for the picture I just gave you. So I'm just going to skip it. All right. So while before we were snark proving the snark verifier, now we're going to snark prove the accumulation verifier. So specifically, we want to prove, like, we want to have a new construction that says, give me the prover and verifier of the snark and the prover verifier and decider accumulation scheme. I want to construct the IVC prover and IVC verifier. Similarly to before, the crux of the construction is going to be some recursive computation R that, again, will check that new output satisfies the IVC transition function, and also the prior output and proof were correctly accumulated. So how does it look? So notice here that before, as input to the recursive circuit R, we had just the next output ZT, but now we also have the next accumulator. And inside the auxiliary input, we find the local witness like before, the prior input and the prior proof like before, but we also have the prior accumulator. Now, like before, we do have to check that we have a correct state transition. That's easy. But now, whenever we are not in the base case, we're going to check that the accumulation verifier establishes that the new accumulator has correctly accumulated the new input and proof into the old accumulator. Okay? I've said the same thing twice. I've said it here, and I've said it here again. Syntactically, this should make sense, because remember, later on, we always have, like, as long as all the accumulation verifiers have been recursively checked, later on, I will only be left with checking the decider. And that's indeed what we see now from the construction of the IVC prover and the IVC verifier. The IVC prover will say, OK, please assemble the recursive computation from the transition function and accumulation verifier. Before running the snark prover, accumulate and produce the new accumulation prover, so the new accumulator. So here we are. I have the old accumulator, the thing I need to accumulate, and I produce a new accumulator. I put it in the auxiliary input. I put it in the input to the circuit. And now I prove that this recursive circuit that we saw above here accepts this input AT and ZT. And now I output, basically as a new proof in the IVC scheme, the snark proof and the accumulator. All right? The IVC verifier, again, will assemble the same recursive computation from the transition function and the accumulation verifier. And now has to check two things. First, we need to make sure the accumulation decider accepts the latest accumulator that we have. Remember, this, if all the accumulations were done in the past were correctly, this is tantamount to simultaneously checking all the snark proofs that were checked. But by checking the snark verifier on this recursive computation, that's exactly what to establish. Like, if this accepts, it means that in the past, we always accepted in the accumulation verifier. So with these two statements, we can infer that all the snark proofs in the past were correct. And here, for R not to blow up in size step after step, we only have to worry about the size of the accumulation verifier. The accumulation decider is only used outside in the IVC verifier, and so it doesn't have to be succinct. So this leads to an updated theorem. Like before, from a security standpoint, if the snark is a snark, namely an adaptive argument of knowledge, and the accumulation scheme is secure. I didn't really go too much into the accumulation scheme security, but that's okay. Then one can prove that the IVC scheme is secure. And here, what we gained is, from an efficiency standpoint, if the snark has accumulation, not succinct verification necessarily, then the IVC scheme is efficient. Namely, it's okay if the snark verifier or the accumulation decider are not succinct. Okay? So we have now relaxed the implication that it suffices of a snark with accumulation to construct IVC and PCD. And also importantly, in this construction, we preserve nice properties like zero knowledge and the type of setup. Okay? So that if you start with a snark, it's a nice snark. For example, with a transparent setup, you will get IVC with a transparent setup. All right.
There is a question from the audience.
Okay.
Is it suitable if I say A0, A1, etc. are internal states?
So I think I tried to answer that earlier here. So I don't really think of the accumulators internal states. You can think about them as basically augmented IVC proofs, right? Before, the IVC proofs only consisted of snark proofs. But now I need to maintain not just the latest snark proof so I can consume it in the next iteration. I need to maintain it also the latest accumulator so I can also consume that one in the next iteration. And what do they represent? Well, it's I don't know, like a good mental picture. Let me just kind of go back to the actual picture. A good mental picture that is not necessarily technically correct is that you can think about basically A2 would be a random linear combination of this statement and this statement, so that you only need to check the random linear combination rather than each of them independently. This is not exactly what's happening because maybe the statement you're proving is not linear. But let's say for linear statements, like this is roughly what would happen. So A2, like A1 would be just this statement. A2 would be like this thing with some random coefficient in front, and you add it to the old one, so that if you want to check the linear statement, it suffices to check this one, because this guy made sure that A2 was a random linear combination of the previous one and the next statement. So they should think of accumulators as a random linear combinations of all the theorems and statements you've seen so far, in such a way that you only need to check the latest linear combination, so it doesn't really blow up. So hopefully that helps with the mental picture. Now that said, accumulation schemes are not so easy to construct. I will not discuss much about that in this talk. All right, so that's all I wanted to say about accumulation. Let me say a little bit about post-quantum security. There's also there's some interesting considerations here from a technical perspective. Okay, first, it should probably go without saying that if you start with a snark that is not post-quantum secure, then recursing it is not going to give you IVC that is post-quantum secure, right? So that we have no hope. But let's say that we did start from a snark that is post-quantum secure, and we actually do have post-quantum snarks. For example, the ones that are based just on hash functions. Okay, they can, for example, instantiate using SHA-256 or lattice hash functions. We have such snarks. It would be nice to say that we are able to construct post-quantum IVC. For example, that would allow us to construct post-quantum succinct blockchains. That would be a nice thing. So there is some subtle challenges here in the fact that the malicious prover may be probabilistic. So let me explain why the malicious prover being probabilistic actually is a challenge in security. So let's say that you have some malicious prover PT that outputs the latest claimed output ZT with some proof by T. And we want to argue that because this prover is reasonably successful, there is a history of local witnesses that certify that ZT really is a possible state after T transitions. The way you do this is you apply the proof of knowledge property, and you kind of obtain from the extractor a witness to the statement that was proved. So we have a prior local witness, a prior input, and a prior proof. From this extractor, you're able to produce a new prior prover that produces the previous input and the prior proof. And then you want to apply its own extractor and continue in this way. And over time, by applying proof of knowledge iteratively, you would construct the history that led to ZT. However, there's a problem here. How do I know that when the prover I define from this extractor outputs ZT-1, it is the same ZT-1 that was output by this extractor? If these are probabilistic processes and I run them side by side, they might just answer different things. Now, for classical security, this is not a big deal. You just say, well, fix the same random tape in both cases. So now they're kind of coupled. However, for quantum security, there is no way to couple the random choices. Like a quantum circuit can make up its own randomness, and you can't just look into the quantum circuit and measure what it decided to do. It will kind of make it collapse. So actually, this is a rather technical issue that was addressed only in the past year. And the way you get around it is you define like a notion of post-quantum adaptive knowledge soundness that kind of requires some sort of like way for the extractor and the prover to live in the same probability space. And one can show that this can be fulfilled in certain models. And then it also suffices for the theorems of recursion. And this has been done both for the type of recursion from succinct verification and accumulation, so that we really have like rather comprehensive foundations for post-quantum security of recursion. Okay, so what I've told you is that there are many snarks. First, I said that snarks with succinct verification can lead to recursion. Fortunately, that there are many of them that do. But this leaves out some exciting snarks, for example, the ones in the Halo paper. But these we can actually capture by relaxing the requirement on a snark by merely requiring that a snark has accumulation. We don't really know how far this can be pushed. Maybe one can relax this further. But to a first approximation, currently, almost every interesting snark construction out there can actually lead rather efficiently to recursive proofs, efficiently at least asymptotically. Okay, now I think, I'm almost done here, but I also took some questions. So let me decide what to do depending upon how much time is left. Let me ask Jing. I can either try to...
Yeah, we spent some time answering questions already. So you can take some time in your materials too. We don't need to have a 10-minute Q&A.
So 5 minutes, 10 minutes,
sure.
Just to pace myself. Which of the two? One is less.
5 minutes is better.
5 minutes. Okay, good. It sounds good. I think I have a 5-minute plan. So now, so far, I have only talked about foundations. There is a lot that can be said about what it takes to take the theory that we discussed into constructions that actually do make proofs of proofs of proofs of proofs in a reasonable amount of time and space in the real world. I will just highlight what are the main bottlenecks that you encounter when you try to do that, okay? So I want to explain why recursion is expensive. So first, even in standalone use, in case you've ever worked with snarks, snarks are rather heavyweight primitives. I mean, cryptography is already expensive on its own, but then even within cryptography, there are some things that are quite expensive. And snarks, they are the type of primitive that make snark verification or snark proofs very small, but the snark prover works very hard to give you this great, nice properties. Now, recursive use, proving is only more expensive. Now, this sounds vague, but there's actually very concrete reasons for why that's the case. So here are the two recursive computations that I've already gone through earlier. The recursive computation for snarks that have succinct verifiers, and the recursive computation for snarks that have accumulation. If you kind of look inside both of these, you can spot some sources of inefficiency. The first one is that, okay, you're gonna have to prove the function f, right? And straightforward approaches to resolve, like you have this circularity here, R and R, and straightforward approaches to resolve the circularity actually lead you to do universal simulation of the description of the computation f, which causes big overheads. So you want to try to avoid, because remember, f is inside the description of R, and R has to have itself described inside it, right? So how does R access f inside itself? So straightforward approaches mean that you're going to end up basically employing a universal machine to simulate this, basically parse the description of f and execute it through a simulator. That would be very, very expensive. The other overhead is the fact that proving the snark verifier or accumulation verifier is also expensive. This has to do with basically details of the cryptography, where the language used to express computation within a cryptographic scheme and then the native algebraic objects over which cryptography operates are different. For example, in an elliptic curve, the size of the prime order subgroup is different than the size of the prime order group over which the elliptic curve is defined. These are two different things, okay? So if you try to naively kind of close the loop, you're gonna do basically simulation of different fields, which is very expensive. You're gonna use one field to do arithmetic over another field. Very, very expensive. This has to do with the details of the cryptography. And on its own, if you just basically bulldoze through both of these, you're gonna get basically impractical schemes. What has happened in the past few years, starting with 2013, 2014, is coming up with like clever approaches to circumvent both of these problems. And only once you have circumvented both of these issues, then that is how one is able in practice to obtain rather practical recursion. Okay, I have probably 5 minutes of explaining each of these things. I don't want to go into that right now. I'm going to skip that and say that people have come up with good ideas. And I'm going to go to my summary slide and conclude by saying that in this talk, I discussed why snarks is useful. Remember, you can use them for constructing succinct blockchains, snarks for distributed computations like MapReduce, construct verifiable delay functions. And from a cryptographic perspective, this is captured by the notion of incrementally verifiable computation and more generally proof carrying data. And there are several ways to achieve it. We saw it from succinct verification and from accumulation. I didn't talk about the specific techniques, but here are some keywords. There are some things called preprocessing, elliptic curve cycles, and algebraic hashes. These are the main buzzwords that have been used to achieve practical efficiency for recursive proofs. I hope you found this talk helpful, and I'll be happy to answer any further questions. Thank you.
Thanks, Ali. This is a very interesting work.
Thanks.
I was always trying to learn something about snark and snarks, and this is exactly right. Okay. Some questions of my own. Do you have concrete examples of the function f that people use recursively that we can consider as running examples when think about those type of problems?
Yeah, so let me go back to the maybe picture here. You can think about so let's take the case of a succinct blockchain. What would that computation f be? So imagine that at every node, what you want to prove is that the next block in the blockchain contains a solution to the proof of work. So namely, it has solved the proof of work. In particular, you have added the next hash to the previous hash, right? And also you have hashed into it a tree of transactions, right? So this way you can prove that you can basically make checking proof of work succinct. In every block, you can check succinctly that yes, indeed, this is the total hardness that has been used across all blocks so far, because every time you recurse, you check the prior proof and you check the proof of work, and you keep track in bookkeeping way what is the sum of the hardness of the proof of work that you have checked so far. You can even go further and not just check the proof of work, but you can literally check the whole state transition. So you could say, I have also checked that I have a commitment to a state, and I have applied to this state all the transactions inside this block, and the state has changed correctly. So for example, I would check that the first transaction in the block is, I don't know, payment from Alice to Bob, and then I would update the state correctly according to that. And then I process the next one and the next one and the next one. This is one much bigger NP statement, but the point is that this can be done. And then now the proof that you have so far wouldn't just certify the proof of work so far, but actually the semantic state transition of the application running on the proof of work consensus protocol. And actually, there are current projects that actually do this. I mean, not exactly like this, but they do have the property that if you check the latest proof, you actually have checked succinctly all the state transitions and the consensus information that happened in the past so far. This gives you extremely lightweight client synchronization.
Interesting. Well, listening to your example, I was thinking maybe another example could be in when we talk about smart contracts, and a lot of smart contracts may be repeatedly and recursively called again and again, and the privacy, those things can be used in compactify those information.
Yeah, no, I agree. So you could imagine a situation where you kind of smear a contract of execution, maybe by different people across different state transitions. And this is like some ongoing computation, maybe within the ongoing computation of the blockchain. And that one could be like a smaller segment of recursive proofs within the larger kind of blockchain computation. And this way, you would never be in a situation where within the same block, everybody would have to come together to collaborate on the same snark proof, but you could just kind of not quite delegate, but just have different people incrementally compute the final correctness proof of some multi-user sequential smart contract execution.
Interesting. We have two questions from the audience. The first is that could we transfer the recursive proof protocol to VDF?
So you can construct verifiable delay functions from incrementally verifiable computation, and actually there are deployed today, wait, let me take a step back. You can get verifiable delay functions as is just from snarks. You just prove that some sequential, some iterated hash function was done correctly. What you can get additionally from incrementally verifiable computation is this notion of continuous verifiable delay functions. So it means that you can compute the function and also compute it further because you always have a proof so far. I haven't seen yet some deployments of VDFs from IVC. There are deployments of VDFs from snarks, but I presume that as sort of recursive proofs become more and more efficient, I think constructing continuous VDFs from IVC in the real world would become practical. I wouldn't say we're quite there yet.
I see.
Primarily because in VDFs, you really need like a very close gap between native execution and proving.
I see. Related to the question, somebody asked the particular Youngzerk function. I don't know how to pronounce that.
Which function? Sorry. Can you write it, maybe?
It is in the message channel. I can send it to you. PIETRZAK. Oh, so this is this is a specific type of a verifiable delay function. So, right. The question is whether this function fits the definition.
I haven't checked. I think let me propose maybe a two-step way to verify that. First, you would have to check whether that function fits the notion of a continuous VDF. If it does, then I presume that a continuous VDF is a very special case of IVC with additional requirements on efficiency. Remember, IVC on its own doesn't particularly care too much about what happens native execution versus verification, right? VDF says that not only you need to produce the output, we need to produce the output together with its proof, right? In a way that is sequential. So here you would need to somehow argue that the proving process is also sequential because the underlying thing you're proving is sequential. Iterated hash function invocation. But so what I'm saying is like IVC as a definition is reminiscent of continuous VDFs, but like you need to actually do a step to go there. But I think that to answer this question, first try to see whether Piechak's function is fits a continuous VDF, and if so, then probably that's like a special case of IVC that satisfies additional properties around efficiency. So there are connections, but they're not like the same thing in general between IVC and continuous VDFs. Thank you for the question.
Thanks, Sally. I hope this answered the question for the audience. I think we're out of time, and we will conclude here. Thanks, Ali, again. This is very exciting work.
Thank you for the attention, and bye-bye. Yeah.
See you.